So 18, we're given some information about an arc length, a radius, and a angle. So the first thing I'm going to observe is that my angle is in degrees. So the arc length formula I need to use is the arc length formula in degrees. So it has the extra pi over 180 tacked on the end. So all I'm going to do now is solve for r. So I can plug in my value for s and my value for theta. Okay, so far so good. So I'll divide by 118 and then multiply by 180 over pi to move everything onto the other side. Okay with what I did there? Now it's just calculator time. So the mode of my calculator doesn't matter. So I'll do 5.89 times 180, and I'm going to put that whole numerator in parentheses. The numerator doesn't really need to be in parentheses, but the denominator sure as heck does. I'll have 118 times pi, all in parentheses. So there I get about 286. Is that okay? Yep. And I can't remember if it was 2 decimal places or 3 hundredths. Okay, so that was right. And then you said the other one you want to talk about was 19?
Yeah, I just got confused, like, what's the word for?
Sure. So let's start with some vocab. It says 2 concentric circles. What does concentric mean? Yeah, that they share the same center. So you have something that looks like this. So far, so good? Cut by the same angle. So we'll draw an angle in here. Sound okay there with the picture? It says the radius of the smaller circle is 4.3. Actually, let's use letters here and we'll write the numbers in later. So that's R1 there. And it says the arc cut, or the cut arc, measures 5.2. So that's just that S. And I'm going to call these R1 and R2 and S1 and S2. Is that okay with my nomenclature there, Ames? Okay. It says the radius of the larger circle is also 5.2. And it asks for the length of that cut arc. So far, so good? So here's the key observation, is that for both situations, we have the same theta. Right? The angle involved for arc 1 and arc 2 is the same angle. So what I'm going to do is I'm going to use the information from the small circle to solve for the angle in the large circle. And I'm going to, just for the sake of simplicity, get my answer in radians. It doesn't really matter, but it just makes the formulas easier to deal with if I use the radian version. So there's my answer for theta. Now, since it's the same theta, I can use that theta along with my value for R2 to solve for S2. Do you guys need to turn the lights out? Is it too hard to see? If it is, feel free to stand up and just like flick out the lights. No biggie to me. But I know sometimes in the afternoon when the sun's real bright like this, it can be hard to see, especially for you guys in the back. So I get 629. And I think these were all in inches. Amy, is that okay? Okay. If it's not, like, we can elaborate or we can clarify.
I was just like wondering where the formula came from, but I see it now. I was just like wasn't sure if it was so tall or not, but now I see
Oh,
it, so.
yeah. So if we're involving arcs, when you hear that word arc, or involving a circle specifically, you're probably going to be using this S equals R theta, which relates, again, what it's relating is, so S is your arc length. Oops. So that's that distance. R is your radius. And then theta is this angle measure. Again, that's what that formula is relating together. It's basically just a way to prorate the circumference of a circle, right? Your circumference of a circle is 2 pi r, right? If you don't want the entire circumference, you're just going to say, okay, what's the angle formed, the central angle formed by that section that I want the circumference for? And I multiply by that number, divide by 360, which is all we're really doing here. So we're just kind of prorating the circumference for that little piece. 629? 6.29. Aiden.
Could you do number 22?
Yeah, 22 is probably the toughest one here. What's up, Zach? Of course. So 22 was probably the toughest one, and it's really trickier than anything else. So it says 2 toy racetracks form concentric circles. So I'll start by kind of drawing a picture here. So there's my concentric circles-ish. It says each track is divided into 15 identical sections. I'm not going to bother to draw all 15 of them since they're identical. I'm just going to kind of draw one of them. It says if the inside car travels 1.2 centimeters less than the outer car on each piece of track, so I'm going to call this piece S1 and this piece S2. And I know that S1 is S2 minus 1.2. And then it asks how much bigger is the radius of the outside track compared to the inside track. So we'll call this radius R1 and this radius R2. It says set up 2 equations using the arc length formula and use substitution to solve. So, okay, so I say S1 is equal to R1 theta and S2 is equal to R2 theta. So we have to figure out theta straight away. It's the same theta in both equations. And it turns out this theta is actually pretty easy to get because I know that theta in this circle is 360 degrees.
And then divide by 50.
And I've split it into 15 identical sections, exactly right. So that's going to be 24 degrees. So we'll actually, I suppose we can tack on the conversion factor then, since we're going to deal with things in degrees. You could have also done radians also, but that's probably just as easy to do it that way. So far, so good?
Yeah.
Okay. Now, if you look here, it appears that in our system we have 4 variables, but only 2 equations, right? That's a problem. You should remember from your Algebra 2 class last year, to solve a system of equations, you need the same number of equations as you do variables, right? Well, here's the catch, and here's the tricky part. It doesn't actually ask us to find R1 and R2. It just asks us to find the difference between R1 and R2. So what I'm going to do is I'm going to just take equation 1 and equation 2, and I'm going to subtract equation 1 from equation 2. So when I do that, on the left-hand side, I have S2 minus S1. And on the right-hand side, I have R2 theta times pi over 180 minus R1 theta times pi over 180. So far, so good. Okay. And I noticed that the theta times pi over 180 is the same in each of these, so I can like factor that out. And I might as well put the 24 in for theta as long as I'm at it. So far, so good. Now, S2 minus S1, I can get from right here. Right? If I add 1.2 to both sides and then subtract S1 from both sides, I get that S1 or S2 minus S1 is 1.2. And then I can divide by 24 and multiply by pi over 180. Or I'm sorry, 180 over pi.
Yeah.
And then in just a moment, I'll show you the alternative way of thinking about this that's actually considerably easier, but I don't think is the reason why it works is a little bit harder to see. So that's 286. And then what units? These were centimeters. Sorry. Is that okay, Aiden?
Yeah.
So sneaky in that you're not actually finding the R2 and R1 separately. You're finding the difference. Now I want to point out to you maybe the easier way to solve it algebraically, but is the more complicated way geometrically. To do that, I'm going to illustrate to you like why this thing is true. So let's say we have some circle. Let's say we have this. Let's put an angle measure onto that. And let's put a arc length measure onto that. And what I'm going to do is I'm just going to change the size of this circle, but I'm going to keep the angle measure the same, and I'm going to watch what happens here. Oh, that's not what I wanted to do. Is it this one that I need to drag? No. What was I going to do in this before? No, that is changing. I wanted to lock that. How did I do that before? I had this work before. All right, well, I don't know how to forget how to do that. All right, well, I'll just talk about the observation here. So let's just say we have our circle, right? And we have our theta here. So if I want to talk about this S1 and R1, and say I want to talk about this S2 and this R2, I know that like theta is equal to S1 over R1. And I know that theta is also equal to like S2 over R2. So how do I want to say this? All right, let me just get to the point here, and then we'll talk about after why it's true. That's probably going to be easier. Let me just do this. Here's the easiest way to do this. Not the intended way, but the easiest way. I'm just going to pick a value for S1. Say S1 is 1. That makes S2 2.2, right? Since I know it's 1.2 longer than S1.
Yeah.
And I know that theta is still 24 degrees, right?
Yeah.
So now I can solve for R1 and R2 separately and just subtract them. Now, why was it okay to just fix this at 1? That's what I was trying to get at. As long as these two things are, like you can, if...
Like it'll be proportional even if you make it like bigger.
Yeah, that's because that arc length formula is fixed.
Yeah.
It doesn't really matter what you pick for those arc lengths. If you know that like one is this much bigger than the other one, you just pick a value.
Yeah.
Non-zero value, right? But, or I should say a positive value. Has to be positive. You can't pick 0 or negative, but like no one's gonna pick like -5 for your arc length, I hope. Lily thought that was funny. Anyways, does that feel a bit better on 22? So again, like the algebraic way to do it got a little complicated, but if you made that realization that like, oh, I can't find R1 and R2 separately, I have to find their difference, that was the big key to being able to kind of unlock that puzzle. Although it still was quite a leap there. It's not easy to see that initially what to do. The other way of just saying, oh, well, what if I just make this specific instead of really vague in general and just fix a value for S1 and then follow everything through? A little bit more doable, simple algebraically. And also it will work. So that's okay to do also. follow-ups to 22 before we move on and take the next person's question? Okay. Sergio, did I see your hand?
Yeah, number
29? Certainly. So 29 says, assume that theta is an acute angle in a right triangle. Okay. Satisfying the given conditions, find the values for the other 5 trig functions. So in 29, we're said that sine theta is 4/7. So here, I know that sine is opposite over hypotenuse. Relative to this theta, this side is the opposite side, so its length has to be 4. This side is the hypotenuse, so that side has to be 7. So far, so good?
Yeah.
I can find the third side then using the Pythagorean theorem. So I'm just going to call this side B for the sake of giving it a name. So remember, when you're setting up the Pythagorean theorem, the hypotenuse must be the C, right? The square of the, or the sum of the legs squared is the hypotenuse squared. So 49 minus 16 is 33. So B is the square root of 33. And then from here, I know then that this adjacent side is the square root of 33. And now it's just like 25 through 28. So cosine is adjacent. That's the square root of 33 over hypotenuse. Tangent is opposite over adjacent. But we don't want to leave the radical in the denominator. Remember, we said if there was the square root was just a number, we were going to rationalize the denominators. And then cosecant is hypotenuse over opposite. It's just the reciprocal of sine. So 7/4. Secant is hypotenuse over adjacent. That's the reciprocal of cosine. But we got to rationalize that denominator. And cotangent is adjacent over opposite, or the reciprocal of tangent. So that's that.
Yeah, I just didn't think about, I think the first part is where I got screwed up.
Yeah, just realizing that it's
Realizing that, like, oh.
that's giving you the opposite and adjacent sides, and then yeah. Yep. But that's the key there, is just turning it into a triangle. Amers. 33. Okay. So it says find the exact value without using your calculator. So if we're going to do that without using our calculator, we know we're going to have to be using either a 30, 60, 90 triangle or a 45, 45, 90 triangle. I'll draw those again for us. And this would be something you'd probably want to have memorized, as these come up quite a bit in this course. Everybody okay with those two rules? So the first thing I want to do is I want to figure out, is pi over 3 a 30, 60, or 45 degree angle? So I'm just going to convert that to degrees. So it's a 60 degree. Okay with that? So cosecant of pi over 3 is the reciprocal of sine. So it's going to be hypotenuse over opposite. So in the 60-degree case, the opposite is x root 3. And the hypotenuse, well, that's always that. The x's cancel. And then when we rationalize our denominator, I have 2 root 3 over 3. Does that feel okay, Amy?
Yep.
You're welcome. So the key there was just starting by unpacking the radian measure into degrees so you knew which of the 2 special triangles you were going to have to use. But for all of 31 through 34, you're going to be using one of those special right triangles. And again, those would be good things to have memorized. The trick for the 30, 60, 90 is that the leg with the square root 3 on it is next to the 30 because they both have 3's in it. That's the way I remember it. Amy?
Just one more thing. For like,
You can ask more than one more
for
thing.
example, for number 37
Yes.
and 38, when you're plugging that into the calculator, do you put like either sine, cosine, or tangent minus 1? Is that what it was?
So yeah, let's talk about this. So 37 will do. So cosecant of 0.34. First thing you'd want to make sure that is your calculator needs to be in radian mode, since you're given a radian measure there. Or you could convert 0.34 into a degree, but like just use your calculator mode. It's going to be faster than turning it into degrees or whatever. So cosecant is the reciprocal of sine. So you'd be wanting 1 over sine of 0.34. So if I go to my calculator, make sure I'm in radian mode. That's good. And then we'll do 1 over sine of 0.34. So that's basically 3. This is the same thing as doing sine of 0.34 and then putting the -1 at the end. That's the same thing. What it's not the same as is sine inverse of 0.34. Okay, so you see the difference in terms of getting it into your calculator. So 1 over sine, fine. Sine of, and then the reciprocal at the end, fine. Sine inverse of, wrong. Is that cool?
Yep.
So sine inverse is a name of a new function. That's not the same thing as 1 over sine. Of course. So this is 1,000. So that was what, 2999? So write that down eventually here. What else do you guys want to talk about? Natalie?
Can you just do number 9?
Sure. So 3 pi over 7. Okay. So to convert from degrees to radians, the way I like to think about this is I know I have like 3 pi over 7 radians. So I'm going to put the radians on the bottom and then the degrees on top. So the radians cancel out just like our unit conversion would. And then the pi's will cancel. So really I have 3 times 180 divided by 7. So that's not going to give me a whole number. So I'll just type into my calculator to get the decimal. 7714. You're welcome. And really, you could have gone straight from the beginning. You could have canceled the pies on the calculator too. If you did left the pies in there, the calculator would take care of them too. But like, I'm about getting rid of them. Kaylee, no, yes, Kaylee.
When you're converting from degrees to radians, does it matter if we put our answer in like terms of decimals or terms of radians?
So you mean in terms of pi?
Yeah. That's
So it would just depend on what the directions are asking for.
right. Okay, and then could you show us how to like get your answer, like if you had it in radians to get it to terms of pi?
I can show you how to get I can take the degrees and write it in terms of pi. Yes. So let's just do, say, number 1, for example. So here we're going to multiply 180 or 80 by pi over 180, right? So what I'm going to do is I'm going to just do this on my calculator. I'm going to ignore the pi. So I'm just going to do 80 divided by 180. And then I'll press the math button and choose the fraction command. That gives me the fraction 4/9. And then I'll just stick the pi back in the numerator because that's where the pi was. Is that okay? Alternatively, you could like reduce the fraction as you go, right? I can take out a 10 from both of them. Then I can take out a 2 from both of these. And there's my 4/9. But like, who has time to reduce fractions by hand, right? Like, get out of here. The calculator can handle it for me. Drake, you had your hand up?
Could you do numbers 40 and 42 if that's not finished?
Yeah, sure. So 40, we have the right triangle, and we're given some information about it. So I'm going to just write in the information that we've given and just what we're looking for. Cool with that?
Yep.
Okay. So what I'm going to do is I'm going to think about, okay, this is the angle that I know I have to use because that's the only angle I know. Relative to that angle, this side is opposite and this side is adjacent. Good with that?
Yep.
The trig function that involves opposite and adjacent is tangent. So I'm going to say tan of 88 equals opposite over adjacent. To solve for a, I'll multiply both sides by a to get it out of the fraction. Remember that tan 88 is just like a, like a stupid decimal. So I'm just going to treat it like a number would. And then I can divide both sides by tan 88. And I guess you could have turned like tan 88 into a decimal straight from the beginning. But I would be cautious about the rounding there. If you're going to do like several steps in that calculation with a decimal, you're probably going to round it several times and like potentially end up with an answer that's pretty far off, as opposed to just waiting until it's time to put it in your calculator and then doing it all at once, kind of the way that I've written this. Now, before I do this, I'm going to make sure that my mode is in degree mode. Since this is in 88 degrees, I need to make sure that I change from radian to degree. I had it in radian earlier. So, oh, that's a small number. I guess that's right, because it's almost the right angle. So I get 0.07 is a pretty stupid number. So the mode button is right next to the blue on button. And then if you look, there's the third option is radian versus degree. So you just move your cursor and press enter on the one you want it to change to. Whatever's highlighted is the mode it's currently in. Loretta? Of course. You're welcome. Drake, are you happy with what we did there?
Yep.
Okay, that's a pretty silly answer, but if we think about it, like this is 88 degrees, this one would be 2 degrees, And we know that the side lengths are proportional to the angle measure that it's across from. So like that side A is going to be awful tiny. So yeah, I guess that makes some sense then. You know what I mean? You said the other one you wanted to look at was 44?
42.
42, okay. It was a 40-something even. Okay. And we're given B, and then A, and we're looking for C. Okay, same idea. This is the angle that we know, so it's the one that we're going to work with. Relative to that angle, this side is the adjacent, and this side is the hypotenuse. So this time the trig function I want to use is cosine. So cosine is adjacent over hypotenuse. And then we'll multiply both sides by C to get rid of the fraction. And then divide both sides by cosine 71. Again, that's just like a yucky decimal. And then it's calculator time. I don't have to worry about putting it in degree mode this time because I just did that before. So there I get 5529. Does that feel okay, Drake?
Yeah.
Okay. Amy? So when I looked at the 71, relative to the 71, the side I knew was the adjacent side. And the side I wanted to find was the hypotenuse. So the trig function that involves adjacent and hypotenuse is cosine. So it depends on what you're given, right? Like which angle you're working from and what sides you know and are looking for. Elvis? 44? Sure. So 44 says find the values of two different angles coterminal with the given angle. So let's just take a moment and refresh what we mean by coterminal. So in section 3, we defined a new way to describe an angle called the standard form for an angle. What we did is we placed the vertex at the origin. One arm of our angle lies on the positive x-axis, and the other arm of our angle rotates however many degrees through. So like 120 degrees would be over here somewhere. We call this arm the initial side, and this side the terminal side. So if I have another angle that does this for rotations, we'd say that that's coterminal to the other one because the terminal sides lay in the same location. So what we notice is basically I'm going to go a full time around and then do the 120 again. So to find something that's coterminal, we can either add or subtract 360 degrees. Now, 44, the angle that we have in question, is in radians. So the radian equivalent of 360 degrees is 2 pi. Remember, our conversion factor is 180 degrees is equal to 1 pi. So 360 degrees has to equal 2 pi, right? So to get a positive angle that's coterminal to this, I'm just going to add 2 pi. So to add these two fractions, I need to make a common denominator, and that common denominator is obviously going to be 7. So I have like 2 pi over 7 plus 14 pi over 7, which gives me 16 pi over 7. And then to find one negative, well, I know I'm going to need to be subtracting. So here I'll subtract 2 pi. And again, got to make a common denominator. So 7 again. So I have 2 pi over 7 minus 14 pi over 7. So that's going to be negative 12 pi over 7. So there's a positive and a negative. If for whatever reason, when I did that and theta 2, when I subtracted the 2 pi, I didn't get a negative number, what would I do? I just subtract 2 pi again. And keep doing that until I got a negative, right? Every time you add or subtract 2 pi, you get another coterminal angle, so you can do it as many times as you need to get the number you're looking for. And just FYI, like I did all that by hand on the paper, but if you just forget about the pi's, you could do 2/7 plus 2, and then use the fraction command, and it'll give you the 16 over 7, and you just slap a pi on at the end, and let your calculator handle the fractions for you. You can do that also. Jack.
Can you do 17?
Sure. Elvis, you happy with what we did there?
Yeah.
Okay. 17. Okay. So here, again, we're given, we don't know what S is. We know that R is 2.1 meters, and we know theta is 40 degrees. Because our angle is in degrees, I know that I need to use the arc length formula with the conversion factor in it. So now I'm just going to fill in my values. And type it in my calculator. And I got, oh my goodness, look what I did. Hachimachi. I did 180 over pi instead of pi over 180. Great googly moogly. That's a heck of a typo, Mr. Kulik. That's better. So 1.46 or 1.4, I guess 1.47. I think these ask for 2 decimal places. And the unit here was meters. Jack, you happy there?
So for the pi over 180, how did you know to use that?
Because the angle was in radian, or in degrees, excuse me.
Oh, okay, yeah.
So if it was in radians, I don't need it, but degrees I do.
Okay. Thank you.
Yeah, you're welcome. Paul.
Can you do number 23, please?
Sure. So 23 is one of these unit conversion problems, not too different than the one from the example. I will point out that I think the answer key doesn't give the correct answer. I think in the answer key we have an answer for meter or in inches per second rather than, or revolutions per second rather than revolutions per minute.
Yeah.
So like it just has the wrong answer there.
It has like, are you at terminal number 22? Or no, 23?
Yeah.
Yeah, it has like RPS.
Yeah, so
you
it's
you times that by 60. Or
right. So I want to point that out before I solve this, that the answer in the answer key is incorrect because it's did the wrong unit conversion. I mean, it's still the right. It's still but it's like how tall are you in feet? 1.76 meters. It's like, so that's probably your height, but it's not the unit I asked for. The same thing here. It's the right, it's just the wrong unit kind of thing. But we'll do this one from scratch. I just want to point that out to everybody before we get into this, because somebody pointed out, we figured that out in the last class, that like, oh, well, that's annoying. All right, anyways, Danny is riding his bike that has 22-inch diameter wheels. And says if you can ride 14 miles per hour, how many revolutions per minute are the tires making? So the key here is that one revolution is the same as one circumference for the tire, which in this case is the diameter times pi, so 22 pi inches. And that's going to be my key from converting linear distance, like miles, into a revolution. Anyways, I think I want to end up in RPMs, right? Revolutions per minute, I think is what it asked for. So first thing I'll do is convert hours to minutes. So I know that the units have to be in diagonal. So hours is going to go on top. And there's 60 minutes in an hour. Next, I'm going to work on converting miles to revolutions. Well, I know to get to revolutions, I need to be in inches. So I guess let's start doing that. So I don't know how many miles are in an inch, but I know that there's 5,280 feet in 1 mile. And then I know in 1 foot, there's 12 inches. So now if we look at what's happened, we're in minutes and then inches. Is that cool so far, Paul? And then to get this the rest of the way, I know there's 22 pi inches in 1 revolution. So that ought to do it for me. So I'm just going to multiply this into my calculator. I'm going to put the numerator all in one line. I'm going to ignore the ones because obviously multiplying by 1 doesn't do anything. And then I'll put the whole denominator in one line. So I'm going to put a parenthesis around this stuff. The denominator is the only place that the parenthesis really matters. The numerator, it doesn't, but I do it to get in the habit of it. So I do that, I get 213.904. And I think if you had the book's answers in revolutions per second, so if you had done that and included another divide by 60, there's the answer in the book is the 356, I think. So if you had the 213.9, you answered the question correctly. Because I don't know what happened. I don't know if the question changed or the answer changed, and who did the editing miss the change, though, one way or the other. You know what I mean? Natalie.
I have a question. When this is a more clarification.
Sure.
question.
Yeah, go ahead.
When you use radian mode and degree mode again.
Okay. So radian and degree mode only matters if you're doing sine, cosine, tangent. Okay? If you're doing sine of 30 degrees, it should be in degree mode. If you're doing sine of pi over 7 radians, it should be in radian mode. So it really depends on whether the angle measure you're using is represented in degrees or radians, and you have to use sine, cosine, or tangent.
Okay.
Is that? Okay. Amy, did I see your hand up?
No.
No. I saw a figment of my imagination. That's okay. Yes, Zach.
You number 24.
Sure. So 24, quite similar to 23. It's another one of these dimensional analysis problems. So it says the circular saw has a diameter of 8.25 inches, and there's 12 teeth per inch on the blade. And it says if it spins at 3,500 RPM, how many cutting teeth cross the surface each second? So basically, I want to take 3,500 RPMs, and convert it into teeth per second. Okay, so I'm going to start with the 3,500 revolutions per 1 minute. And I guess I would start by converting minutes to seconds. That's easy to do right away. So I know 1 minute is 60 seconds. And you're good with the units have to be diagonal from one another, right? That's how I know minutes is on top? Okay. Well, I know that 1 revolution is equal to 1 circumference. And in this case, that's going to be 8.25 pi inches. So again, we'll look at where we've gotten to. We're in inches per second, right? So the last thing I know is that there's 12 teeth per inch. So that'll give me now teeth per second. And it's just time to type her into my old calculator. And this is going to be a big old number here, huh? Oops. So 18,143, I guess. I guess it doesn't tell me how to round this. Oops. Nope, that wasn't right. 143. Is that cool, Zach?
I got 290.
Yeah, I was gonna say, that's good.
Well, I'm pretty positive this number is the correct number. So do 221?
Can you go back to the calculator?
Yeah, sure. So I had the numerator, 3,500 times 8.25 pi times 12. And then oops, divided by 60. The mode shouldn't matter on this because you didn't use sine, cosine, or tangent.
Yeah, I don't know what I got.
Okay. Well, I can look at your calculator later and we'll see if we can figure it out.
Okay.
But it sounds like your mistake was a common one because somebody else said they got that, didn't they?
Yeah, I just forgot to put in pi.
Oh,
Because I thought it said close to. Now I got it.
I see. So Amy said she forgot the pi on the 8.25. Did
I
you?
think I did my circumference math wrong.
Oh, that could be. Sergio?
Can you look at my computer for a second? It's just like not. I like just bought a new keyboard 3 days ago, just not having it.
Oh.
Like the trackpad's working, but I can't type. Try it. I'm so confused. I literally just bought this thing. It was $125.
Wait, you had an extra?
No, keyboard.
Oh, no. Worth it.
Should I take an IT?
You may.
Okay.
Yeah. But let's wait till the end of class, okay?
Okay.
All right, Zach.
I was looking at my math. When I was getting the circumference, I did 2 pi r. Or no.
That's
2
2 pi r is fine. That's the same thing as pi times d.
So I got 0.5. I don't know what I did.
Okay.
2
8
times
point,
pi.
yeah, 8.25 times pi is going to be about 25.
And then, yeah, I don't know what I did then.
So that sounds about right for the circumference. I know that's not very satisfying. Did you do something? Yeah, I don't know. Did you forget to? I don't know.
I think the problem was, I kind of like broke apart my problem. I figured out how many revolutions there were, and I was trying to figure out how many keep the revolution and then did it, instead of like doing one in phrase like you did.
Yeah.
And I just think that's what my problem was.
Maybe you divided the wrong way or something.
Yeah.
Yeah. All right. I need you guys